All right, last homework problem on homework 1, which is properties, equations of state, phase diagrams, steam tables, all that good stuff, ideal gas. This last one is more of a calculation-y problem. Kind of some concepts in here too, though. Okay. So this is not out of the book. This is one that I stole from Dr. Kenneth Benjamin, but I like it. It says, calculate the van der Waals parameters, A and B, from the critical point data for these three species. So I've got CH3OH, I've got CH3CH3, ethane, methanol, and then CH3H, methane. Okay. So, well, I'm calculating stuff. So, okay, I need to write down some equations. And I need to write down some assumptions. I'm assuming that van der Waals EOS is kosher. Or valid. Something like that. Okay. A is equal to, what is it, 27 over 64th. Let's see here. RTC quantity squared over PC. B is equal to 1/8. Times RTC over PC. Okay, I'm going to look those up for each one. Okay, or maybe, possibly, I have a code that looks those things up for me or calculates A and B for me. If that you do, great. Just, tell me what A and B equal. As long as you write down the formula, I'm happy. So you write down the formula, definitely. Okay? Now, I am going to not actually calculate them, I'm going to ballpark things though, okay? So let's see here. So let's go to our tables. So it's chapter, it's not chapter, it's Appendix A is the first table. Let me roll the critical stuff. Okay, so the first thing we have is methane. So it has a critical temperature of 190 and a critical pressure of 46. Okay, so let's see here. Methane is, let's just write this down quick. So we have about 190 over 46, because everything else is going to be the same. Okay, so for our ethane, we're going to have 48.74. And the temperature, though, is 305. So a little higher pressure, but a whole lot higher temperature. And then the methanol is probably going to be pretty darn high, too. Oh, it's 80. So it's a little bit higher, it's a lot higher pressure, but it's also a lot higher temperature, 512.6. Okay, so let's see here. Again, let's just kind of ballpark things. So 190 divided by 45. Oh, that's going to be about, maybe 4.1. Okay. 305 divided by 48. Well, that's going to be about 6. Okay. Yeah, something like that. Okay. And then 512 divided by 80. Let's see here. That's going to be about also a little bit more than 6, so about 6.3. It's going to be a little bit higher. Not a lot, a little bit. Okay. In terms of the B. Now, in terms of the A, okay, so our, we call this, we're going to call this alcohol, ethane, and methane. So alcohol, ethane, methane, the B value, so the alcohol is about 6.3, this one's about 6, and this one's definitely about 4.1. Okay, now, if we look at A, well, the dividing thing is, but it's, the top is squared. So this one, it's really, okay, this one's horrifically huge. So, this one's definitely big. This one's somewhere in the middle, and then this one is small. Okay. So our B's are about the same. A and E are a little bit bigger. Okay. But the A is the alcohol definitively has a higher A value, okay, because the squared aspect. All right. Now, using the values calculated above, so again, you're going to calculate them and give me values, okay. For part A, B, and C. Okay, so D says compare the van der Waals parameters between the methanol and the ethane. Explain the relative magnitudes of A, B from a physical basis. Okay, so these are about the same. This is much, much bigger than that one. Okay, so that's really what I'm trying to explain. Now, again, we're looking at this from a molecular perspective and all these other things. But we have to remember what A and B represent. So what does B represent? B represents the excluded volume. Because remember, in van der Waals, it's RT over V minus B. And this, as a whole, is the hard sphere repulsion. Repulsion. Okay? So that term is the repulsion term. Okay? And it's saying, as my volume of my molecules is bigger, because that's what B represents, that I'm going to repel a lot more, because I'm going to have a number minus a big number, meaning so a number minus a big number is a small number, okay? And a number divided by a small number is a big number. So a big volume, a big exclusion volume means a big repulsion. Okay, so the alcohol is a little bit bigger. Okay. Or pretty darn close. Does that make sense? Heck yeah. Two heavies. In fact, looking at my math, maybe my math is wrong. Maybe that is a little bit bigger. I'd actually have to calculate that thing. But they're pretty darn close. Now, why is that? Well, because size-wise, they're about the same. They have two heavy atoms. The heavy atoms pretty much tell you how big something is. And now, things that are more electronegative are going to take up smaller space. So, thinking about that, yeah, my numbers are probably wrong. This one should be a bit bigger than this one because the carbon's going to take up a little bit more space, and because there's 3 hydrogens versus 1, that's also going to take up a little bit more space. The other thing is that the bond is going to be shorter because of electronegativity, so it's going to take up a little more space that way because the carbon-carbon bond is going to be a little bit longer than the carbon-oxygen bond. So really, those numbers that I ballparked are probably wrong. Okay. Really, the alcohol is probably slightly smaller because of those reasons. What are those reasons again? Well, same amount of heavy atoms, oxygen's more electronegative. Electronegative things take up less space. They also have shorter bonds, and so all those things added together are going to take up less space as a molecule. Okay, that makes sense. Okay, but now let's look at A. Okay, and A says, well, that's the attractive component. A over V squared. That's the attractive energy, so to speak. Okay, and so if I look at the A's between the two, well, holy snot, the alcohol is much, much bigger than the ethane. Why is that? Well, attractive. Well, what did we talk about how things interact? Well, there's polarity. Is alcohol polar? Yes. Is ethane polar? No. Now, does it being polar mean it's repulsive? No, it just means it's not as attractive. It's indifferent. It's like, okay, hi. Whereas the alcohol is like, hey there. So there's an attraction associated with polarity, okay? The other thing is it's hydrogen bonds. And not only does it hydrogen bond, it can hydrogen bond with itself. It's a donor and an acceptor. Maybe a moderate one, maybe a mild one, who knows, but it definitely is hydrogen bonding with each other, whereas the ethane is strictly interacting through van der Waals. Now they are both interacting with about the same amount of van der Waals, because they're about the same size. But that alcohol has all of that attraction built into its hydrogen bonding and its polarity. More attraction means a much bigger A value. So that makes total sense in this case. Now, part E says, compare, what does it say? Compare the CH3 and the CH4. So I'm comparing the ethane to the methane. Okay, well, again, B is the size. Well, hydrogen's much smaller than a CH3. Okay, that's no-brainer. Okay. It says it's about 2/3 the size. Well, that's, I mean, it's got half the heavy atoms, but not exactly half the hydrogen. So 2/3. Okay, maybe that makes sense. Who knows? Okay. And then the interaction energy. Okay, well that one is, you know, it's much smaller because, I mean, the critical pressure is about the same, so really I'm squaring it by half, so it's like a quarter, it should be about a quarter of, the A value should be about a quarter, okay. Now, does that make sense? Well, what's A? It's the attraction energy, okay. So let's look at how it's interacting, okay. Is it polar? No, they're both nonpolar. So that means they're both non-hydrogen bonding. So now it's van der Waals contacts. Shape, packing. Well, I've got 2 heavy atoms to touch versus 1 heavy atom to touch. Now remember, van der Waals is all about touching. So those of you who like to sleep with your blanket, do you want to sleep with a dish towel or a real towel? You want to sleep with a, I mean, if that's all you have a dish towel and you have like a bath towel or a beach towel, you're going to choose the beach towel because it's bigger. You can have more surface area sharing between you and the towel if it's bigger. Same thing here. We have ethane. Look at all that shared space versus methane. So much more shared there. Now, to what degree? Well, about 4 times as much. Okay. But that is why it's a little bit more attractive. Okay. Now, one might argue, well, isn't this kind of a backwards argument? Yeah, it kind of is. I mean, the reason it has such a high critical temperature is because it has such a high attraction. But, you know, this is kind of a chicken and the egg thing. You know, when it comes down to it, though, it really, I mean, you know, I can calculate an A and I can calculate a B. You know, I mean, I can look at the critical temperature and the critical pressure, but there is that nuance of it being squared versus not squared, and that has, you know, like it, you know, it kind of showed there that, like, okay, the size was about the same between the methanol and the ethane, but the interactions were completely different. Okay. And so, and I can say this, I would have never known that the size was about the same by looking at the critical pressure and critical temperature alone. Okay. I had to kind of calculate the B to see how similar they were. So, so that's the end of homework.